Assalamualaikum and hello everyone. Today we are going to present our FAC1004 project about geometric extremes in the complex plane. In this project, we study a circle and an ellipse and we find the minimum and maximum values of modulus and argument. We solve this project in two ways, which are manual calculation and GeoGebra verification. Our presentation starts with the circle, then the ellipse, and ends with comparison between the algebraic and visual results.
To begin, we have defined our circular locus with a center z0 at 3 plus 4i and a radius of 2. My task is to convert this complex form into a Cartesian equation. By substituting z with x plus yi, we need to apply the modulus definition. We isolate the real and imaginary component, then square both sides to eliminate the radical. This expansion results in the standard Cartesian form of a circle. This rigorous manual proof provides the foundation for our boundary analysis. I will now hand it over to our modulus lead, who will use this equation to find the exact extrema point relative to the origin.
Now that we have defined our Cartesian locus, I will identify the modulus extremus, Z-min and Z-max. In engineering, this represents the closest and furthest points on our boundary relative to the origin. Algebraically, we define a line passing through the origin and the center of the locus Z0. Since this line is a normal to the circle, its intersection points with our locus naturally provide the minimum and maximum distances. So, by solving the simultaneous equations between this line and our circle, we obtain two specific complex numbers. We label the point nearest to the origin as Z-min and the furthest away as Z-max. To be mathematically rigorous, we verify this using the general vector form.
We are finding the boundaries of the angle for a circle in the complex plane. Think of it this way: any complex number z on our circle creates a ray from the origin. The smallest and largest angles these rays make are where the rays are perfectly tangent to the circle. To find this, we substitute the line equation y equals to mx into our circle's Cartesian equation. This gives us a quadratic in x. Since tangent line only touches the circle once, we set the discriminant to 0. Solving for m gives us the two critical slopes. By taking the inverse tangent of these slopes, we find the exact range, the minimum and maximum arguments for the entire locus. This method provides us a rigorous algebraic proof for what we can see geometrically. Now back to the team.
To conclude part A, we compared our manual algebraic proof with our visual model. Our derived Cartesian equation matches the plotted circle exactly. The values for the minimum modulus of 3 and maximum modulus of 7 were visually confirmed by our sweeping circles, which intersect the locus at the precisely calculated points Z-min and Z-max. Finally, the tangent rays y equals 0.57x and y equals 4.23x verify our argument extrema, providing a complete double proof for our investigation.
Everyone, I am the lead for the ellipse Cartesian conversion. My goal is to transform a complex focus into a standard XY equation. I have defined our ellipse with horizontal foci at -2 and +2 and a major axis length of 6. This gives us the starting focus, the modulus of z plus 2 plus the modulus of z minus 2 equals 6. The methods I convert this, we substitute z for x plus I y and use the isolate and square method. By moving one radical to the y and squaring both sides, we eliminate the first root. After simplifying the linear terms, we isolate the remaining radical and square at a time to clear all the roots. Finally, by arranging the terms and dividing by the constant, we arrive at our standard form: x squared over 9 plus y squared over 5 equals 1.
Next, starting with the modulus, we find the distance from the origin by substituting the ellipse equation into the distance formula and differentiating it. We locate the stationary points. This confirms our maximum distance is 3 along the x-axis and minimum distance of Z5 along the y-axis. For the argument, we look at angle theta. We use the tangent ray method y equal to mx and set the discriminant to 0. Since the ellipse surrounds the origin, the argument spans around the full range from the minimum -pi to the maximum pi. Finally, we apply implicit differentiation to the standard form. This gives us the gradient dy over ds equal to negative 5f over 9y. This derivative confirms exactly where the horizontal and vertical tangent occurs, providing a perfect check for our extrema results.
In our analysis of the ellipse, our manual isolate and square derivation perfectly aligns with the GeoGebra model. The algebraic results for the minimum modulus of Z5 and maximum of 3 are visually confirmed by sweeping circles that touch the locus at 0, plus minus Z5, and plus minus 3, 0. Furthermore, the absence of real solutions for the tangent discriminant in our notes correctly matches the GeoGebra visual, proving the origin is internal to the locus.